Okay, everyone. I know there's only 14 as compared to 25 of us earlier. A little technical problem. Thanks for coming back. Again, my name is Mr. JP Rene. I'm helping out with 832 in Rockland, and we're going to talk about maps and charts today. So next slide. So basically, what I wanted to do today was a bit of review of nav 1 and 2. We'll probably skip that, seeing as how we're going a little late right now. We'll talk about maps and charts and their elements. We'll talk about properties of maps, scales, relief, and I'll show you some aviation charts and a few of the publications. So it's not a long class, but it will give you a heads up on the types of maps we use for flying. Next slide, please. So as a review, these are some questions. I was going to quiz everyone on these for a few minutes as we start the class. But basically, we'd like to know, please understand what the difference is between parallels of latitude and meridians of longitude. You might want to know what the difference is between a great circle and a rhumb line. And you may want to help understand how to calculate variation, deviation, and change from a true to magnetic heading. So your acronym TVDMC, you might want to remember that. So next slide. So those are some of the review questions, and you might want to brush up on that for any kind of midterm or upcoming exams. So what are maps and charts? So maps are basically a representation of an area on the planet. The planet is round, and the representation of this round globe on a flat piece of paper is called a map. A chart, on the other hand, is something we use for navigation. So it'll have an orientation that lets us know north and south. It'll have distances. It'll have geographic points and coordinates to help us navigate. So those are the difference between a map and a chart. But generally, we use those two terms interchangeably. We use them to mean the same thing. So next slide. So there's four basic elements to any kind of chart. One is the area. So we'll have the map will have a certain scale. So we could have a map of Canada, or we can have a map of just Ontario, or we could have a chart of simply the St. Lawrence Seaway. So depending on what we're looking for. Obviously different shapes. Some can be rectangular, some are square. Charts will also have bearings and geographical coordinates and distances. So we'll have scales there as well. Next slide. So depending on the type of map we want, and depending on the type of chart we want, we have to project the sphere of the planet onto a piece of paper to be able to get a proper representation of the area we want. So there's three types of projections. Okay, big test questions here maybe. So Lambert conformal conic projection, Mercator projection, and transverse Mercator. And I'll talk about these in the next slide. So next slide. So the Lambert conformal conic projection is kind of taking the globe and putting a cone over a certain region of the globe. That cone, when we unravel it, now becomes your chart or your map. So some of the properties for this type of projection is the meridians of longitude kind of converge together and meet up at the pole, okay? The parallels of latitude become curved and they become concave as they get closer to the pole. The scale is very good. It's very uniform across the area that's depicted, okay? And a line drawn on this type of map is a pretty good estimate for a great circle route, okay? But there's some, next slide, please. The other projection is a Mercator projection. No, so instead of taking a cone, we'll take a cylinder and we'll draw a line, in this case, around the equator. And then basically the flat cylinder, once it's flat, gives you your chart. But you can see on the slide, countries like the USA seem very small as compared to Greenland or Antarctica down at the southern part of the chart. So there's some problems in distortion when you have different types of projections, okay? However, all the area close to the equator, the part that's closest to where the sphere is touching the planet, so in this case, the equator, that would be very, very precise, okay? Next slide, please. So in this case, the Mercator projection, the meridians of longitude are straight up and down, nice and parallel, okay? The parallels of latitude are also straight and parallel, okay? But unfortunately, there's no constant scale, okay? There's a lot of distortion, like I said, in the northern parts, so like close to the North Pole and close to Antarctica, okay? But distances where the projection is focused on, so in this case, the equator, are very, very precise. Okay, next slide. The third projection is a transverse Mercator. So we have our planet, and the tube that we would use to make the chart, we've simply turned it 90 degrees. Now the line touching the projection or the chart is not the equator, but it is a specific meridian of longitude, okay? So in this case, if we were to roll out the map, the area of that red line on the slide going through Canada, the USA, Mexico, would be very, very precise. So if that was, let's say, the 100th meridian going through Nunavut and Manitoba, we'd have very, very precise, accurate scale there. However, east and west would be very, very distorted. Okay, so three types of projections: Lambert conformal conic, Mercator, and transverse Mercator. Next slide. So most charts, most maps have common properties or common themes or common issues or factors that link them together that make them all look like maps. One, they all represent some portion of the Earth. It could be the North Pole, could be a country, could be part of the ocean, okay? They all have longitude and latitude. They all have scale relief and isogonic lines or contour lines. And we'll talk about those three a little later on today. Obviously, a map or a chart for navigation purposes, we need to identify towns, cities, roads, railways, airports, okay? Restricted areas. But a map will also have a compass rose. So one section on the map indicating north or south, okay? And if it's an aviation chart or aviation map, it'll have aeronautical information. If you're in the Navy or if you're in the Merchant Marine, you'll have a nautical map and it'll have nautical information. So next slide, please. One of the most important things is scale. We want to know how large an area, how big the map is, okay? So one thing we like to do for scale is we like to give it a fraction and a graduated scale. So we'll use something like that diagram that I'll have 1 or 2 bars to show distance, to show the scale, and to show a statement of equivalency. So typically a map will say 1 inch on this map equals so many inches or so many miles in the real world. So if I were to use this one, the scale is 1 in 500,000. That means 1 inch on this map would be 500,000 inches on the planet. Okay. On the map, we'll have different bars, different scales showing either nautical miles, kilometers, or statute miles. And then we'll have a statement of equivalency that'll say 1 inch equals 7.9 miles. So in this case, 1 inch is also 500,000 inches. Well, those 500,000 inches equal 7.9 miles. Yeah, so the scale, and typically a scale will be off to the side or at the bottom of a chart. So I have a chart with me here. This is an aviation chart. And as I open it up, I can see that on the side, and I'll try and show you on the camera, you can see I have the graduated scale up here, and it'll help me measure out where I'm going on the chart. So scale is also tells me how large or how small the chart actually is. So in this slide, we have 1 in 50,000 and a 1 in 250,000 chart. So the 1 in 50 would mean 1 inch on this map would equal to 50,000 inches, okay? This is a picture of Rockland, and you can see Clarence Creek off in the bottom there. In the 1 in 50,000, we'll see the roads, we'll see the towns, we can see green areas that will show typically forests, blue lines will be rivers or lakes, but you can also see the black dots, and the black dots will be actually individual little houses or buildings. Okay, so that's a fairly precise, fairly accurate map used for navigation. The 1 in 250, you can see is a similar area, showing Rockland and Clarence Creek, similar kind of roads, similar offset between north and south. But you can see we seem a lot higher. We can see more of the river, we can see more towns. So a 1 in 50 is just a zoom out of what we had at the 1 in 50. And for aviation, we typically use a 1 in 500. So again, we'll even be zoomed out even a bit more. Okay, so the ratio is your scale. It tells you how big or how small your map is. Next slide. Another thing we have on maps is relief, is to show, because yes, the planet is round and the earth is sort of flat sometimes, but we also have lakes, we have mountains, we have rolling terrain. So in order to show that relief, okay, in the ground elevation, we'll use 3 types of, three formats on a map to help show elevation, okay? So layer tinting, contour lines, and spot heights. So next slide, we'll talk about layer tinting. So layer tinting is basically trying to establish certain elevations and associate a color. So in this case, in the diagram up on the top, you can see that even the ocean is colored into 3 different shades. They're dark blue, light blue, and sort of white. So those would indicate 3 different depths of water. So maybe 0 to 10 feet, 10 feet to 100 feet, and 100 feet and deeper. On land, it's kind of the same thing. We're going from green to light green to white to yellow, orange, and brown, those show different elevations. So maybe 0 to 100 feet, 100 to 500, and so on. And depending on the color that you would have on your map would tell you how high the nearest elevation is. The bottom picture is just another example. It's just another layer tinting code that could be used. And if I were to have one on these maps, I'll have a quick look. Yeah, we have some. It's pretty small. It's basically right here. There's only 2 because, well, we're in Ontario and it's not that high. If we had a map of BC, we'd have a lot more colors to show. Next slide. Another way to show elevation are contour lines. So these contour lines are lines of equal elevation or equal altitude over the ground. Okay, so as you can see in the 2 pictures, we have this mountain and it's kind of cut. If we look at the mountain sideways, we kind of cut it in layers, kind of like a cake, I guess. And each altitude has a line. But if we were to take this mountain and look at it from the top, all we would see are these rings of equal lines. Okay, what's important to note is with these rings of equal lines, the closer the rings are, the steeper it is. So as you can see in the bottom diagram, the hill, as we look at the hill, the slope on the left side of the hill is fairly steep. It's a lot steeper than the slope on the right side of the hill. So if we were to look at the same diagram, the same hill on the bottom, we see the circles. You can see how the contour lines are all tight together. That tells you that the hill is fairly steep there. And where the lines are further spaced apart would indicate that the slope is more gradual. Next slide. So here we're looking at a top view of 2 hills or 2 mountains and a small river. So the hills, we've got one hill called the Mount and another hill called the Weather Law. And we've got the Deer Hope River running through in between them. So you can see the contour lines. You can see where there's some areas they're quite tight and some areas are further spaced apart. Another point or another way to indicate terrain or elevation is by the use of spot heights. So here we have 2 spot heights, one at 447, it's just a small dot and a number, and another one at the Mount. There's the dot at the top of the hill and a number, 43 or 538. That would be the elevation. Now, on the chat, could anyone find another spot height for me? Top left, yeah. And what's the altitude of that spot height there? $519, perfect. Can someone find another spot height? Have a look, bottom right. Yeah, 464, perfect. Okay, so if we were hiking from Deer Hope to either the Mount or to Weather Law, what would be the steepest climb? What would be the hardest climb? Anyone can type it into the chat. If you were to look at the contour lines, remember, really, contour lines really tight together indicates very steep terrain, and contour lines that are spaced out would be gradual, a more gradual slope. So what's the steeper climb? To Weather Law from Deer Hope or from Deer Hope to the Mount? Yeah, the Mount. Very good, Sergeant Yan. Okay, next slide. Okay, code word for this is, what's this helicopter or that bird? Anyone? Cormorant. Very good. Next slide. Boom, cormorant. Okay, types of aviation charts. I've shown you two. I have three here. Okay. One is a VFR, so Visual Flight Rules Navigation Chart. That's one of these. And if you look at the screen, it can be fairly long. And if you look at the diagram, they cover most areas of Canada. Okay, actually, they cover the entire country. So each square there is one VFR navigation chart. Okay, and yeah, they're about this big. They're on both sides, and they're used for aviation. VFR terminal area charts are similar type of maps, but a bit more detailed, a bit more zoomed in, and they're used for terminal areas, so our large airports. And so there's only 7 of those really. And then there's IFR charts, again, similar chart, except they're generally black, white, and green, and they're used for instrument flying. So pilots flying commercial business jets or airliners like Air Canada and WestJet will use those kind of maps. Next slide. So we'll just talk about these 3 maps a little bit. So the VNCs, so VFR navigation chart, VNCs, the scale is 1 in 500,000, okay? They depict a large geographical area, okay? As you can see, as we saw on that picture, there's about probably 40 for all of Canada, okay? As I showed you, their charts are printed on both sides. They'll show aviation. They have a lot of aviation information. They have scales. They have directions and radio frequencies for airports, okay? You'll get them at most flying clubs or flying schools. You'll see there's lots of aeronautical information on the chart itself. They're all named a certain name for a certain area. So this one's obviously of Toronto, okay? They're based on the Lambert conformal conic projection, okay? And these are used for flights at lower altitudes or slower aircraft. Next slide. So those are VFR navigation charts. They're called VNCs for short. Next slide is VTAs. Like I said, a little more zoomed in. They're more important because now we're really talking about specific areas closer to airports. They're based on transverse Mercator because we really want an accurate location, okay? Again, these are also printed on, typically printed on one side, okay? But on the other side, we'll have airspace information as well, okay? So those are VFR, so Visual Flight Rules terminal area charts, but in short, we call them VTAs. And just for giggles, I tossed in the instrument flight rules chart. So next slide. These are used for instrument flying. They have altitudes, radio navigation aids, and how to get from point A to point B. But basically, you need, once you have your basic licenses, you need instrument training, you need an instrument test. Your aircraft has to be certified and equipped with the proper instruments to fly. And so once you have all this, this is basically the charts that those flying on instruments will use. So that's it for the types of aviation charts we'll use. Next slide, we'll just talk about 2 types of publications. We're almost done. So one publication you might have heard the other instructors talk about, especially maybe in Theory of Flight or Air Law, is the TC Aeronautical Information Manual, okay? The website link is down at the bottom of the slide. It covers pretty much everything that's in from the ground up and more, everything we talk about, meteorology, navigation, radios, air law, all of that is lumped into this big book. It's a fairly thick book, but it's free, it's online. You can see the little white box. Those are the topics that it covers. So if you're really serious about a career in aviation, that's one of the manuals. It's a really good reference manual when you're studying. The other book that we've got, give me 30 seconds. It's called a CFS, Canadian Flight Supplement. Okay, this is a book that is fairly thick. Okay, but it has a whole bunch of information on Canadian aerodromes. Actually, every airport and aerodrome in Canada is listed in here. It gives information on navigation aids, radio frequencies, runway services or airport services, runway conditions, and stuff like that. So again, this is another valuable manual for our publication for pilots. Unfortunately, it's not on the website, but you can get them through Nav Canada. And I think that's about it. So I have a few questions. So what are the 4 basic elements of the chart? And someone can either speak up or type it in the chat. Go ahead, Flight Corporal.
Would it be area, shape, bearing, and distance?
Yeah, awesome. Okay. What are the 3 types of map projections? Anyone can type them up in the chat. 3 types of map projections. Yeah, so Lambert, conic, conformal, sure. Mercator, yeah, and transverse Mercator. Close enough. We'll give you the points. 2 types of aviation charts. V for VFR. Gave you the first letter. Come on. Still waiting on the chat. VNC, yes. That's these bad boys here. Yep. And VTA, yes. Oh yeah, and then we also have the IFR ones as well. Okay, finally, 3 ways to show relief on a chart. To show either elevation, color, some kind of lines. How do I? Layer tinting, yes. Spot heights, yes. Contour lines, yes. Okay, great. That's it, everyone. Hey, really sorry about the technical glitch and really sorry I had to drop about half of you tonight. Hopefully we'll be able to get everyone else to either listen in on the presentation. If you have any questions, I'll stay on for a little bit. You can ask me through the chat or on audio. But for everyone who came back, thank you very much. Hope you learned a little bit tonight, and good luck for the rest of your course. And that's it. If you have any questions, you can stay on. If not, off you go. Have a good night, and we'll talk to you guys later. Thanks, Eileen. You're a great Vanna White.
You're very welcome.